Hello, everybody. It's been a while since I've posted, almost a year, in fact. The last one that I posted of the topic that I'm going to talk about was a year ago. And that was titled LC95 and Heat and What We Don't Know We Don't Have. And if you go back and look at that video, one of the things that I was talking about in there was the fact that the way that we use the retardant in relation to the fire bridge concept, I was explaining the problems that we have with just using retardant only, especially if we're not going to try to cool the active flame front. Well, as true as that is, in my belief and opinion, one of the other things that I think that we need to take serious consideration and a second look or a first good hard look is some of the problems that we're having with retardant. Now, again, this is my opinion on how I look at this. So I don't expect you to believe it. I don't expect you to follow it. But nonetheless, if we want to be true students of fire, because fire is dynamic, our education and our self-training should be equally dynamic. So with that, if we go back to the LC95 and heat and what we don't know we don't have video that I did on YouTube channel, I stated in there that I agreed with the Forest Service and Phos-Chek that the retardant is every bit as effective dry as it is wet, insofar as it being a burn inhibitor. Well, there's some information that I've looked at in my trek of really studying the capabilities of retardant, what's in it, what its chemical makeup is. So I'm not a chemist, but I think some of the things that I have found that I'm going to present to you right now in this short video is going to be pretty eye-opening. There's some things that have forced me to reevaluate that statement that I made based upon reports like this one. And there's another one. But this one right here, USDA Forest Service research paper INT-121, 1972. Now, this paper right here is written by the research scientist Charles W. George and Elmer D. Blakely, and it's titled The Effects of Ammonium Sulfate and Ammonium Phosphate on Flammability. So it goes back to 1972, so it's about 54 years ago, somewhere in that neighborhood. But one of the things that caught my attention was the fact that he states in his introduction the problem. Now, the problem that he says is that, and I'm going to read a little bit so you understand where I'm going and why I'm bringing this to you, especially when we start looking at what's going on with retardants and how we seem to have a retardant use only policy nationally, at least outside of helicopters and the fire boss, the 802 fire bosses. That seems to be typically the first go-to. We think it's the end-all, be-all, the badass of the stuff that's out there. This report, in conjunction with what some folks have called me, texted me, emailed me over the past couple of years, and I've been looking at this for 6 years. So ever since July of 2018, ever since the Hot Pot fire and then the Martin fire here in Nevada, I've been looking at it pretty significantly. So let me read what the scientist says here. The most commonly used active retardant chemicals are ammonium sulfate and ammonium phosphate. These chemicals, when applied to cellulose fuels, alter the combustion process to produce less flammable products while increasing the amount of non-flammable products. That's the current standard spiel that we all believe. So now, the most efficient use of these chemicals can only be made after thorough quantification of their effects on flammability. Let me read that again. The most efficient use of these chemicals can only be made after thorough quantification of their effects on flammability. Now, flammability is defined as the interaction of ignitability, sustainability, and combustibility. This goes back to Anderson report of 1970. Ignitability is the ease with which a fuel will ignite. Under given conditions, the most ignitable fuel will ignite with the least energy input. Now, I'm going to read that part one more time as well because it's going to come up and it's going to be pretty significant in the next paragraph. So the ignitability or sustainability is a measure of how well the fuel will continue to burn with or without the heat source after ignition. Okay? Ignitability is the ease with which a fuel will ignite. Okay? Combustibility is a measure of the rapidity with which energy is released from the fuel following ignition. And I'm going to have links to these two reports up on my website. Fire retardant chemicals are often applied to reduce the overall flammability of fuels. Period. In other instances, the chemicals are used specifically to reduce the sustainability or combustibility. Here's the critical part. It is often thought that ignitability is decreased by treating fuel with retardant chemicals such as ammonium sulfate and ammonium phosphate. However, recent empirical data indicate the reverse. That is, less energy is necessary for ignition of treated fuel. This fact is substantiated by more sophisticated thermal analysis data, which indicate that treated cellulose undergoes pyrolysis and combustion at lower temperatures with less energy inputs than does untreated cellulose. That was George and Sussett in 1971. Pyrolysis is the thermal degradation of a material. Now, let me move on to research paper from 1971, which this one was before the one that I just read you. So 1971. That one was published in 1972. Now, on the page, in the introduction, they have a section here where they talk about the definition of pyrolysis. So page 1 in the introduction, which, by the way, this report is titled, okay, Effects of Ammonium Phosphate and Sulfate on the Pyrolysis and Combustion of Cellulose. So everybody's big on this pyrolysis effect. There's a problem with that, in my opinion. Again, all this is just my opinion. Nobody's endorsing this. Nobody's sanctioning this. This is just my opinion for the last 6 years, from 2018 to present day. The last 6 years of studying nothing but why do we keep using something that's a fertilizer that's supposed to help something grow, but yet you never see anything green after we drop it. Okay, and I'm not an advocate against retardant, but I think there's a way that we can use retardant to be more successful with it. So, the purpose of this study, again, the 1971 report, before what I just read you, the purpose of the study was to provide extensive thermal analysis data that could be used to categorize the effects of these retardant chemicals on the pyrolysis and combustion of cellulose. So, they've got a superscript number 2 there that points to the footnote. So the number 2 footnote is, for the purpose of this paper, pyrolysis is defined as the degradation of a material in an inert atmosphere or vacuum. Let me say that again, folks. Pyrolysis is the degradation of a material in an inert atmosphere or vacuum. You following me? Combustion refers to the process taking place when the material, as well as its degradation products, are in contact with oxygen or air. Now, let's go to the next page. So you can see here that they've got the test apparatus. You can see the guy standing there over the 2-pin plotter or data recorder and whatnot. And then down below they talk about pyrolysis. Okay, so let me read this to you. So pyrolysis was studied in a nitrogen atmosphere at a flow rate of 100 cubic centimeters per minute, period. Not even being conducted in the atmosphere to which we fight fires in. A similar flow rate of air was used in investigations of combustion. For samples pyrolyzed in nitrogen, the percent of weight remaining as a function of sample temperature was monitored. For combustion analysis, an alternate method of recording data was needed due to the highly exothermic character of the reaction. So, if we go back to that report, okay, and we have to understand something here, that the pyrolysis, from what I can understand from 54-plus-year-old reports, is that the idea behind the testing and the retardants was to come up with something that, hey, ideally, if we can, and this is just what I put together in my own head, so if they could come up with something that could basically allow charring, and if you look at the chemical composition, that if you have a polymerized substance with the phosphate at a certain temperature mixing, the byproduct becomes water. Okay, well, here's the problem that I see with it, just using critical thinking, is that the temperatures to which they use here are never going to be what we face in the real world. So the water vapor is going to evaporate far faster than the beneficial effects can be. And then if we're infusing this fuel, this biomass, that if you will, with a retardant that, according to the report, reduces the temperature required to ignite it, but then at the other side is more exothermic. As for those of you that don't know, endothermic means that it will absorb heat. Exothermic means that it generates heat. And it just said right here, for combustion analysis, an alternative method of recording data was needed due to highly exothermic character of the reaction. And then it goes into the test apparatus and how they did it, et cetera, et cetera. Now, in this report, they used a specimen size of 0.021 by 0.021 by 3 inches in length. So we're talking about something that is is over half of a 1/16 of an inch in diameter smaller. So a 1/16 of an inch is 0.0625 thousandths of an inch, 62.5 thousandths of an inch. We're talking about something that's basically 21 thousandths of an inch in diameter by 3 inches long. These are the test specimens that the report says that they were doing this on. So the point that I want to leave you guys with, food for thought, is A, we don't breathe 100% nitrogen. Number two, if this planet did not contain any nitrogen, everything here would be in a giant oxidizer, and we would be one backfiring automobile away from complete poof. So consider that. So when they have to infuse the burn chamber or the combustion chamber with nitrogen to control the reaction, that is not indicative of what we are dealing with in the real wildland fire environment. There's also from the California State University down in, I think it's Los Angeles, and I can pull it up. And again, I will have links to all of this and on the website. And it's the metals in wildfire suppressants. Now, some of you may have heard about this, the Hotshot Wake Up podcast. Tim over there, he covered this. However, he's got the link on his site, and I'll put the link on my site as well. But it talks about heavy metals in wildland fires, wildland fire retardants. Now, The interesting thing about that is like, okay, so the toxicity of the retardants talks about being anywhere from, well, first of all, they categorize the retardant as a hazardous waste. However, it says that the ranges of the toxicity are anywhere from 4 to 2,800 times greater than the U.S. EPA safe drinking water limitations. Okay, so that's there. Okay, it might be some cancer issues or whatever, but what we've got is chromium, cadmium, arsenic, lead, copper, vanadium, manganese, barium, thallium, and the other one, let me get my periodic table here, antimony. Now, I've also done some serious checking in this, and I covered this in the video a little bit last year because I was talking about some of the products that off gases, phosphoric acid, pneumonia, and then once you get above 500 degrees centigrade, you run the risk of possibly generating hydrogen gas due to what's called ammonia cracking. Now, ammonia cracking is the industrial form of creating hydrogen from ammonia, and you use a catalyst like nickel to lower the temperature to make the process more efficient. So the food for thought that I want to leave you guys with all of this, and I'm not going to keep dragging this out, but I want to leave you with enough to where it's like, okay, if you're going to use retardant, I strongly suggest that due to the exothermic nature of the retardant above 932 degrees Fahrenheit, and running the risk of phosphoric acid, ammonia, and then separating to hydrogen, and then the problems that the heavy metals begin to react at elevated temperatures, you might want to cool it first with water. Hence, all this stuff does is reinforce my belief and opinion that the FireBridge concept is determine what the BTU output is of your fire. Get your fire line length. Use water. There's plenty of areas on my firebridge.substack.com page that you can pick up the information and materials. You can be a free subscriber. I don't charge for that. And it will tell you how to use nomograms. A lot of people say, well, nomograms are antiquated and outdated. Well, you know what? Behave Plus software is better in determining all the variables for the energy output, but it still doesn't tell you what you need in cooling capacity. So if you want to take advantage of the retardant and be more successful, you have to get it below those thresholds of being able to cool your fire to where the retardant can be more effective. You're going to have less of a likelihood of generating the toxic gases, which I believe is what happens, or the flammable gases, and then have your crews in place. When you read some of my reports, I say like, oh, well, you need 7 or 8 or 10 aircraft, in some cases 15, depending on the size. I already know that that's impossible, but that's talking about if you got like, let's say, a mile-long fire line, you want to put the entire mile out in 1 second of time, of linear time, then that's what you need. Of course, you're not going to be able to do that. So segment it, prioritize a line, say, okay, well, we've got a lat and 4 seats. Okay, great. Well, load them all up with water and then go out there and cool it. But have your crews standing by, have your dozers already in position. Think about where this thing is going to go with the rate of spread. Put your forces out there, get your control lines, and then as it's approaching, time it. Prioritize where it's going to be and segment it out. Instead of doing a mobile attack with engines, you're doing a mobile attack with aircraft. But do it sequentially. If you're doing it one at a time, load and return, then this fire's got time to come back, especially with what we're seeing in Canada and everything else. Things usually get pretty ugly once they heat up. And then the temperatures. Everything is temperature dependent. So keep that in mind. So FireBridge, cool it, retard it, dose it. Time to vent, and it can be done. And if you don't know, then as I've always said, you guys can get a hold of me, and I will take care of things and get you whatever you need.